In this lesson, we are going to start talking about polar coordinates. Now, polar coordinates is a different kind of system of graphing. What we typically use is XY, where we have a horizontal value and a vertical value, and then we look to see where they cross on the grid. Now we're going to talk about polar coordinates, where we're going to have two values that are matched together to find a point on the grid, but these two values are going to mean different things. This R represents what's called the radial coordinate, and this value right here is called the angular coordinate. And these identities here listed is what we'll use to be able to go back and forth between XY ordered pairs and polar ordered pairs. Now, when we look at this point A here, normally what we would look at is we would think of this horizontal line here as the x-axis and this vertical line right here as the y-axis, and we would see where we would come out horizontally and where we would come out vertically, and that would give us our xy point. Now, when we're dealing with polar coordinates, what we're going to do is when we identify this point, instead of coming out x units and go up y units, what we're going to do is we're going to see how far we swing open in terms of either radians or degrees. So in this case, to get to this point A, I'm going to swing open pi over 6 radians or 30 degrees. So I'm going to have that listed as my angular coordinate. Then what we're going to do to see how far out from the center we come out, that will be our value of R, or our radial coordinate. So if you look, I come out 1, 2, 3, 4, 5, 6, 7, 8. So my radial coordinate will be 8. Now, how we get our identities that we see above in the definition, if we look at our angle that we come out, this is our theta, this is the radius, the radial coordinate, and when we think about it in terms of an XY grid, the point here to here shows the distance in X, and this point from here to here shows our distance in Y. So we're looking for our point A here. Now, if we want to find a relationship between x, y, r, and theta so that we can translate back and forth between Cartesian xy points and polar coordinates, what we're going to do is we're going to use trig identities. So this is the center of the graph. This would be like this point right here. And if you think about our identities, if I think about cosine of an angle is adjacent, which would be x, over the hypotenuse, which is r. So if I set up an identity, cosine of theta is equal to x over r, and then I solve that for x, I get that my x coordinate, when I'm looking at xy's, my x coordinate is going to be related to my polar coordinates by taking r times the cosine of the angle. And then using that same argument but with sine, because sine is opposite over hypotenuse, we're going to set up the same thing to show the relationship between y, theta, and r. So we have sine of theta is equal to y over r. And then when we solve for y, we get r sine theta. So this is how we are going to go back and forth between the polar coordinates and the xy coordinates. And one more thing that actually I didn't put down here, but it's up in the definition box up here. Another thing that you can do is use tangent of theta to do opposite over adjacent. So we can also add down here, tangent of theta is y over x. Now, if I swing open pi over 6, here's my origin, and I swing open pi over 6 or 30 degrees, if this 8 was a negative, what would happen is instead of coming out this way, 8 units, I would come out this way, 8 units. So if I made up another point B here, and I call that point B negative 8 pi over 6, that would be out this way here. I would count 1, 2, 3, 4, 5, 6, 7, 8. So that would be here. So now we're going to practice converting back and forth between rectangular and polar coordinates. And one thing that I want to stress before we start doing this is that when we look at XY points, for each of those values on the grid, there's one unique XY representation for that point on the grid. When we're looking at R's and thetas, they are not unique representations for one point. So you have to keep that in mind when you are changing from XY to R thetas, because you need to make sure that you're picking the correct R and the correct theta so you represent that unique point of 1, 1. Okay, so when I go to find my R, the easiest way to do that is just use Pythagorean theorem. Here's my X, here's my Y, and my R is my hypotenuse. So this is the origin. I'm coming out this way. Here's my point 1, 1. So to find my R, I just use Pythagorean theorem. So I have R squared is equal to 1 squared plus 1 squared. So I could get that R is plus or minus square root of 2. Now, when I go to find my angle, we're going to use tangent. I'm going to say tangent of theta is opposite over adjacent. So we're going to do y over x. So in this case, I have tangent of theta is 1. So my angle could be pi over 4 or negative pi over 4. Now, because this point 1, 1 is in the first quadrant, we want to make sure that we're swinging open so that our point lands in the first quadrant. So I don't want to choose negative pi over 4 because that would land us in the fourth quadrant. I want to choose the angle of pi over 4. So that's going to be my angle. And then my R, since I want to swing open this way, pi over 4, I want to come out a positive square root of 2. So this is my R and this is my theta for the point 1, 1 for our X's and Y's. Now, looking at part B, we have negative 3, 4. So this is going to be in the second quadrant. So this is my origin. I come out negative 3, and I go up positive 4. This yellow point right here is my point negative 3, 4. Here's my angle. So to find my R, I'm going to do negative 3 squared plus 4 squared is equal to R squared using Pythagorean theorem. So I'm going to get that R is plus or minus 5. Now when I do inverse tangent to find my angle, I'm going to find tangent of theta is y over x, right? Opposite over adjacent. And when I use my calculator and I do inverse tangent, I'm going to get that I could have an angle of negative 0.92729, or I could have 2.21429. Now, because we're looking at the second quadrant, we want to make sure that our radians for our angle is going to fall between pi over 2 and pi. So that is definitely not this angle. This angle opens up and will land me in the fourth quadrant. So I want to make sure I choose this angle. And so I'm going to swing open this way, 2.21429, and then I'm going to come out 5. So here is our polar coordinates for our Cartesian coordinates, negative 3, 4. For the next point, we're looking at a point that's on the positive y-axis. So I'm going to swing open an angle of pi over 2 and then come up and out 3 units. So this one, we don't have to use Pythagorean theorem. I can just go directly to stating that we swing open pi over 2 and we come out 3. All right, for the next and last part for going from XY points to polar points, we've got 5 square roots of 3 and negative 5. That's going to be in quadrant 4. Here's my origin. I'm going to come out positive 5 square root of 3, and then I'm going to come down negative 5. So here's my point. So I make my rectangle, and to find r, I take 5 square roots of 3 squared. I take -5 squared, and I get 100. So r is going to be plus or minus 10. I forgot my plus and minus here, but r should be plus or minus 10. Now, when I find the angle, I'm going to use inverse tangent. I'm going to say tangent is opposite over adjacent, so -5 over 5 square roots of 3. And you can simplify that as 1 over the square root of 3, negative. And then when I use inverse tangent, I find that I get a decimal representation for pi over 6 or -pi over 6. Now, because we are looking at the fourth quadrant, pi over 6 is going to swing open to the first quadrant. So I want to swing down into the fourth quadrant. So I'm going to use -pi over 6, and then I'm going to come out 10 units. And so my ordered pair in polar format is going to be 10 -pi over 6. For the last 3 parts of the example, we're going to go from polar coordinates to xy coordinates. So for this example, we have an r of 3 and an angle of pi over 3. That's in the first quadrant. So I'm going to use the fact that I know that x is r cosine theta and y is r sine theta. And I'm going to plug in my r's and my thetas, and I'm going to get that x is 3/2 and that sine is 1/2 square root of 3. For the next coordinate, we have an r of 2, and our angle is 3 pi over 2. Now, this is a major angle. This is going to fall right on the negative y-axis. I'm going to open 1/2 pi. So when I plug that in, I can verify it by looking to see that I get a 0 for x, because I'm going to plug in 2 and 3 pi over 2 for r and theta, and I get 2 cosine of 3 pi over 2 is 0. And then for y, I get 2 sine 3 pi over 2 is -2. So visually, when I imagine that I open 3 pi over 2, this is verified by showing that I'm going to fall on the negative y-axis. For this last point, I get an r of 6 and an angle of -5 pi over 6. So when I plug that in to I plug my r in as 6, and I plug my theta in as -5 pi over 6, and I'm going to get that my corresponding x and y values are -3 square roots of 3, and y is -3. And that definitely falls in the third quadrant. And so when I imagine that I open up in the negative direction, -5 pi over 6, that's 1 pi over 6 shy of pi when I open in the negative direction. So that will land me in the third quadrant. So visually, when I think about that, what it looks like on the grid, it's going to both fall in the third quadrant. So this is good. Now we're going to practice actually graphing polar equations. And the equation that we're going to graph is r is equal to 4 sine theta. And just like we would normally make an xy chart, we're going to make a theta r chart. Now, what we're going to do is I would stick with all the major angles and go from 0 to 2 pi. And then you're going to plug in those angles into the equation and get your corresponding value of r. Now, to save yourself some arithmetic here, you can actually do this on the calculator and create this table on the calculator. So you want to go to mode, and you want to make sure, if you're using radians, of course, you want to be in radian mode. And then you want to also make sure you're in polar mode. So you have function, parametric, polar, and sequence. So make sure you're on polar. So then once you have that set up, when you hit your y equals, you're going to see r equals instead of y equals, because now you're in polar mode. And now when you hit your variable button, theta will show up instead of x. Okay, so I'm going to graph this 4 sine theta. Okay, now I'm going to go to my table. Now I want to make sure, since I'm doing this on the calculator, and I want to enter the values for theta and get out my corresponding values for r, I want to make sure that my table is set up to do this. So I am going to click the second button And then above your window button in blue or a different color, it will say table set. So I'm going to choose second window. And I want to make sure on independent, it says ask. So that way the calculator prompts you for your independent variable. And then on dependent, it automatically gives it to you in the next column. So mine's already set up to do that, but make sure that yours is set up like this. So then when you go to your table, I can actually just put in my values for theta and it will give me my corresponding values for r. So if I want to put in 0 for theta, I'm going to type 0 and it's going to give me 0. See how it matches up here? I'm going to put in pi over 6. So I hit second and then this caret button to access my pi and then do divided by 6 and it will tell me it's 2. Here's my 2 here. So it's giving me these corresponding values here. And also another thing to keep in mind too, if you're going to be graphing this by hand, it's better to keep it in decimal value. If you want to write it as an exact value, that's fine. But you might also want to write down the decimal approximation because when you're graphing this by hand, it's hard to tell on the graph where, say, the square root of 11 is or something like that. So it's better to have it in decimal format when you're actually trying to graph this by hand. So you can use your calculator to create your table. Now, once you have your table of values, when you graph it by hand, you're just plotting points and then connecting the dots, just like we normally do. So for this first point here, I would plot an angle of 0, meaning I'm not going to swing open at all, and I'm going to come out 0 units. So that means I'm going to be looking right at the origin. Now at pi over 6, I'm going to come out 2. So here's pi over 6. So I swing open an angle of pi over 6, and I come out 2 units, 1, 2. So that's this point right here. Now, you would just go through and plot those points. One thing that I do want to point out is that some points overlap. So, for example, where we have pi over 2, and I come out 4 units. So here's 0 degrees. I come out pi over 2. That's this angle here works on the positive y-axis. And I come out 4 units. 1, 2, 3, 4. So that's this point right here. If I look at this point right here, I'm going to swing open 3 pi over 2 and then go to negative 4. So here's my 0 degrees. I'm going to swing open 3 pi over 2. So that's on my negative y-axis. Now, so I'm swinging out to this angle right here. But the point says to go negative 4. So rather than come out this direction, I'm going to go this direction. 1, 2, 3, 4. So these 2 points are the same. And this is what I was trying to tell you earlier, is that you could have the same location or the same point on the graph, but it's written in different ways. So the point pi over 2, 4 and the point 3 pi over 2, negative 4 are the same point. They're just written in different ways. It's not unique. So once you plot all those points and you connect the dots, you're going to see that you get a circle with a radius of 2. Now, my artwork here is not the best. It doesn't look like a nice circle, but this is what it's supposed to be. My center is going to be at 0, 2. So here's the center of the circle right here. Let me get my pointer again. So here's the center of my circle. And this is if I'm thinking about it in terms of x, y. So if I'm thinking about it in terms of r and theta, my center is going to be pi over 2, and I come out 2 units. So I swing open pi over 2 and come out 2 units. So that's the center. And then I have a radius of 2. So when you plot points for a polar equation by hand, I recommend using the table on your calculator to save yourself the arithmetic and possible arithmetic errors. And then keep in mind when you're plotting the points by hand that some of those points might overlap. They're not all unique. So now that we plotted it by hand, let's take a look at what this looks like on the graphing calculator. So I know I already have my equation in here. I'm going to start with Zoom 6. Zoom 6 is the standard viewing window where it goes from -10 to 10 on both axes with a scale of 1, and then I can adjust from there. I'm going to go to Zoom 6. Here is my graph. Now, it's a little bit small because it only goes out with a radius of 4. So I'm going to adjust my window. Let's go on a scale of, say, -5 to 5 on both axes rather than -10 to 10. And that way we get a better picture. So you can always adjust your scale by hitting the window button. And then up here, you'll notice it gives you your range for your angle too. So here it says we're starting at an angle of 0 and our max is 2 pi, and it gives a decimal approximation here for 2 pi. So now that I closed it in a little bit, I'm going to hit the graph button and it should look a little bit bigger. Now we're going to look at some basic polar equations and translate them into rectangular coordinates. Okay, the first equation we're going to look at is theta is equal to pi over 3. Now, whenever we have an equation of this format, where we have theta is equal to and then some angle, where r is not identified in the equation anywhere, this is going to be the equation of a line. Now, I want you to think back in college algebra when we talked about vertical and horizontal lines. When we talked about a horizontal line, we identified the equation as y equals and then whatever value it passed through on the y-axis. Let's say y is equal to 5. So in that equation, there are no x's, and that is because y in that equation is not dependent on x. It doesn't matter what the value of x is, no matter what, y is always going to be 5, and hence you have the equation y is equal to 5. So the same idea lies here. Because r is not in this equation, I want you to think about this as r could be anything, and it doesn't matter what r is, you're going to have that the angle is pi over 3. So when we look at the graph, no matter where we come out for the value of r, we're going to have an angle of pi over 3. So for example, let's say I have the point r is equal to -100, and then our angle is pi over 3. So I would swing out pi over 3. -100 means I come out this way 100 units. Okay, so let's say I had +100 with an angle of pi over 3. Then I swing open pi over 3 and I come out this way 100 units. So when you have a polar equation with no r in it, and it's just the angle is equal to, and then you have it in degrees or radians, that is going to be the equation of a line. Now let's take a look and see what this looks like in terms of x and y. So we know that r doesn't matter here. R can be anything, and the angle is always going to be pi over 3. So we're going to set this up where we have tangent of pi over 3 is the opposite over the adjacent. That's our y over x. And the tangent of pi over 3 is the square root of 3. Now, when I do some cross multiplying, I get y is equal to the square root of 3 times x. So here is our line in mx plus b form. Our slope is the square root of 3. And that is because of the way that the angle opens up. Okay, let's look at another basic equation. And just like the one before it, we're missing a variable. We're missing theta in here. We see no theta, so it doesn't matter what theta is. R doesn't depend on theta. It doesn't matter what theta is. The radius, the r, is always going to be 3. So no matter which angle I swing out open, I'm going to come out a radius of 3. And that's what creates this circle. Okay, now, so when I want to put this in rectangular coordinates, I'm going to use r squared is equal to x squared plus y squared. And then I'm going to plug in 3 for r, and I get x squared plus y squared is equal to 9. And here's my equation for the circle. Now, for this next example, I know what this is because I worked it out ahead of time. It's going to be a circle. However, you don't need to know what it is to translate that into XY coordinates. So when you have something that's unknown, you're just going to do some algebra to work it out. So here are the resources that we have. We know that r squared is equal to x squared plus y squared. We know that x is equal to r cosine theta, or we can rearrange it to write it as cosine theta is equal to x over r. And then we also know that y is equal to r sine theta, or sine theta is equal to y over r. So these are the resources that we're going to use when we try to rewrite something from polar coordinates to rectangular, and vice versa. So we start off with our original equation. We have r is equal to 6 cosine theta minus 8 sine theta. I'm trying to use these formulas up here to substitute for r's and thetas, so I have things in terms of x's and y's. So what I'm going to do is I'm going to replace cosine and sine with x over r and y over r. And this is what I get. Now, if I multiply both sides by r, I get r squared is equal to 6x minus 8y. And then I also know I can replace r squared with x squared plus y squared. So now I have x squared plus y squared is equal to 6x minus 8y. Because I've done conic sections before, I recognize this as possibly being a circle or a ellipse. So I'm going to work it in that direction by completing the square. So I'm going to subtract 6x over to the other side, and I'm going to add 8y to the other side, and I'm going to leave a blank so I can complete the square. So here's the complete the square for the x quantity. Here's the complete the square for the y quantity. So whatever I put in here, I have to add it to the other side to keep the equation balanced. So I take half of 6 and square it, that gives me 9. So I put a 9 over here, which means I need to put a 9 on the other side of the equation. For my y term, or my y quantity, I'm going to take half of 8 and square it, that gives me 16, which means I need to put a 16 over here as well. Now, when I add up this side of the equation, I get 25, and I can write that as 5 squared. When I factor this, because I completed the square, I can rewrite that as x minus 3 quantity squared. And when I rewrite this in factored form, I can write that as y plus 4 quantity squared. And I have equals to 25, or 5 squared. This is the equation of a circle. The center is 3, negative 4, and my radius is 5. So when you're trying to translate back and forth between polar coordinates and xy coordinates, these are the equations that you want to use to algebraically manipulate it so that you can get the form that you're looking for. Now, when we scroll down here, I did a cut and paste out of our textbook. These are some of our basic shapes in their standard equations. So we have a line. That's when you have, and we talked about this already, that's when theta is equal to some value and you don't have any r's in the equation. So no matter what your value of r is, you have this angle, and that's going to end up being a line. We have the form of a circle, that's this. A spiral, b theta will give you the spiral, and then a is going to be like a shift. Now, looking at this graph here, this is called a limacon, and it looks kind of like a heart with an inner loop. This here, the cardioid, is actually a special case of the limacon where the A and the B are the same. And then we have a rose, and a rose has these basic equations. The A in front here tells you how far out the petal is this way from the center out. And then the B will help you figure out how many petals you're going to have on the rose. Okay, in this last topic we're going to cover in this lesson, we're going to talk about symmetry. Now, previously, when we would talk about symmetry of functions, and we're talking about rectangular coordinates, and we would talk about symmetry with respect to the y-axis, we would think about if we plug in a negative x into the function and we get the same function back, then you're going to have symmetry with respect to the y-axis, which means it's going to be an even function. Then if we plugged in a negative x into our function and we got out negative f of x, then we have an odd function, meaning there's symmetry about the origin. Lastly, if we talk about symmetry with respect to the x-axis, then that means for every xy point we have on the graph, we have an x negative y, which means it's not going to be a function because it won't pass the vertical line test, but it does indicate symmetry about the x-axis. So in the past, we've talked about symmetry, but now we're going to actually apply it to polar curves. So let's go and look at our definition for symmetry with polar curves. The first symmetry, or the first property, talks about being symmetric about the polar axis. The polar axis is the horizontal axis. So this is talking about symmetry across what we look at as the x-axis. That means for every point r theta on that graph, we should have, since it's symmetry, and this is acting like a mirror, we should have another point on the other side of that polar axis, r negative theta. So in other words, if I swing open theta in the positive direction and I come out r units along the radial axis, I should have that same point on the other side of that horizontal axis by swinging open in the negative direction for the angle and still coming out to a positive value of r. So these two r's would be the same. Now, because we talked about previously the uniqueness of these points, there really isn't any uniqueness of this point. There's many ways to write these points, okay? So another way that you could test is if you look at negative r and pi minus the angle. So if you think of this, let's use an example. Let's say this angle is 3 pi over 4. So I'm swinging open 3 pi over 4. And then I'm coming out a radius of, say, 5, okay? Then I should have this point here, but we can look at it in a different way. We can swing open an angle of pi minus theta. So if this angle here is 3 pi over 4, if I take pi minus 3 pi over 4, that's pi over 4. I'm swinging out to this angle here, to pi over 4, but I'm going in the negative direction along my radial axis. So when I swing open to pi over 4, I'm not coming out this way, I'm coming out this way. And I end up with that point. So another way to write this point is negative r and pi minus theta. So if we replace theta with negative theta and we get the same equation back, or if we replace r with negative r and we replace theta with pi minus theta and we get the same equation back, that's another way that we can check for polar axis symmetry. Looking at the second property, we could have that the curve is symmetric about the pole. And when we talk about the pole, we mean what we think of as the origin. It's the center of the graph. So if for every point r theta on the graph, we have the point r pi plus theta is also on the graph, then we have that pole symmetry. Okay, so let's look at this picture here. When we look at symmetry with respect to the pole, this is what it might look like. Something like this, where for every r theta on the graph, we have a negative r theta on the graph. And another way we could look at, which was just stated in that property, was that you could replace theta with pi plus theta. So if I replace theta with pi plus theta and I get the same equation back, or if I replace r with negative r and I get the same equation back, then we have symmetry with respect to the pole. Okay, let's look at the last property. We could have symmetry where the curve could be symmetric about the vertical line, theta is equal to pi over 2. So that would be what we look at as the y-axis. This is the vertical line, pi is equal to 2. Now, ways that we can test for vertical line symmetry of theta is equal to pi over 2, we could replace theta with pi minus theta and see if we get the same equation back. Or another way we could test is replace r with negative r and theta with negative theta and see if we get the same equation back. All right, so let's use this example here. R is equal to 3 sine 2 theta to look for symmetry. Now, I already did this out ahead of time, so I know what kind of symmetry we have, but I think it's a good idea when you're looking for symmetry, also graph it out. Even if you're not doing it by hand and you just take a look at it on the calculator, it's going to help you verify what you find algebraically. It's kind of a way of doing a self-check. I graph this out by hand and I get a 4-petaled rose. And if we look at this standard equation and we go back and look at that reference sheet I give you with the different kinds of shapes and the different kinds of equations, you'll see that this is going to be an equation for a rose. Now, it's been a while, so don't quote me on this. I'm pretty sure that when you look at the coefficient that's in front of the theta, that's going to help you determine the number of petals. But what I can't remember for sure, and would be a good exercise for you to look this up. I think if the number is even, then you double it to find the number of petals. And I think if it's odd, then it's actually, like if this was a 3, then I think it's actually 3 petals. Now, I could be wrong on that, like I said, but that would be a good exercise for you to check on that. You could Google it. All right, so let's graph this. I'm going to put in 3 sine 2 theta. Remember to make sure you're in polar mode if you're not already there. Now I'm going to use the standard viewing window, so I'm going to hit zoom 6. We can adjust it from there if we need to. So there's our 4-petaled rose. This 3 that's in front, that's going to tell us the length of our petal, how many units it comes out this way. So looking at this graph, to me this looks like it has all 3 symmetries. It looks like it's symmetric about the origin, over the x-axis, and over the y-axis. So if I was doing this for the first time, I would anticipate all 3 symmetries. And this is a good way to check to make sure that you're doing this correctly algebraically. So let's look at the rules and do this algebraically now. If we want to look for symmetry about the polar axis, the first test that we could try is replace theta with negative theta and see what happens. Now, if we plug in negative theta, we get r is equal to 3 sine negative 2 theta. Because sine is an odd function, then I can take this negative here and throw it out in front here in front of the 3. Now, because this doesn't give me the same equation back, I can say that this test is inconclusive. It didn't tell me anything. So let's try the other test. We can replace r with negative r, and we're going to replace theta with pi minus theta. So here's my negative r. I have 3 sine, and I'm going to put in pi minus theta inside here where theta was. And then I'm going to use some algebra to manipulate this. When I distribute this 2, I get 2 pi minus 2 theta. I don't need the 2 pi in there because that just means we've gone around a full cycle. So I can take that out. So I have negative 3 is equal to negative 3 sine 2 theta. And when I divide both sides by negative 1, I get r is equal to 3 sine 2 theta. So this tells me that we do, yes, because we got the same equation back, we have symmetry about the polar axis. Now, let's look at symmetry about the origin, or what is called pole symmetry. Okay, the first thing I'm going to try is replacing r with negative r. So when I do that, you're going to find that it's inconclusive. So then I tried the other test where I replaced theta with theta plus pi. And so I plug in theta plus pi in here for theta. And when I distribute, I get 2 theta plus 2 pi. I can get rid of this because it's just another full cycle. And so I'm left with r is equal to 3 sine 2 theta. So this tells me, yes, we have pole symmetry. And we kind of anticipated this because we looked at the graph ahead of time. All right, now let's look for vertical symmetry, or y-axis symmetry. It's also called pi over 2 symmetry. We're going to try replacing theta with pi minus theta. So when I do that, I'm going to put pi minus theta in here, distribute the 2. So I get r is equal to 3 sine, and then inside here I have 2 pi minus 2 theta. The 2 pi can go away because that's just repeating another full cycle, so we can pull that out. And then let's see, then that leaves me with negative 2 theta inside. And because sine is an odd function, this negative can be removed, and I can replace it with a negative 3 in front. Now, because I didn't get the same thing back as what I started with, this test is inconclusive. So we're going to go on and try the other option. Let's see, for this one, we're going to replace r with negative r and theta with negative theta. When I do that, I get negative r is equal to negative 3 sine 2 theta, because sine is an odd function. This negative can go away, and I can replace it with a negative 3 in front. And then when we divide both sides by negative 1, we get r is equal to 3 sine 2 theta. So using this test, we did show that we get the same thing back. So we do have theta is equal to pi over 2 symmetry, or y-axis symmetry. So one big thing I want to sum up with is, again, because these points are not uniquely described, that is why we have more than one test that we can use here to try. Now, if we test it and it doesn't work, it's just inconclusive.